So here we're going to look at the ratio and the root test, and they're fairly similar. That's why we're doing it at the same time. They almost have the same exact conditions, the same exact conclusions. So all you're doing is taking your sequence that's from inside your series, and you're going to put an n plus 1 in it, you're going to divide it by the regular sequence, and then test out this stuff. I'm just going to let... my dishwasher's done. I'm just going to let this one, these are the conditions, you can write them down, and then I'll do an example. So let's look at an example for the ratio test. So for this, we're going to take a look and use the ratio test. It's actually not that bad. The problems that you're going to run into are just simplifying, really, and it's just algebra. So I'm going to do this, and I'm going to do something involving a factorial for these examples, and then we'll move on from there. So the ratio test says, first, let's get a sub n plus 1. So what does that mean? That means I'm going to take a sub n, and instead of putting in an n everywhere, I'm going to put an n plus 1. That's all it means. So then we have this. And I'm going to take that and divide it by the regular sequence, which is a sub n. And so what do I have? I have 2 to the n plus 1 over n plus 1. And then I take the reciprocal of this and I multiply. N over 2n. And then what do I have? Well, and then now I'm going to try and simplify. So I have here 2 to the n times 2 to the 1. That's exponent rules. Over n plus 1. And I'm just going to keep going. And then 2 to the n there. That cancels with that. So that's nice. And then I just have 2n over n plus 1. Take the limit of this. Actually, we'd actually take the absolute value. So let me write that. As n approaches infinity, the absolute value of 2n. You don't really need to write the absolute value because n is positive anyway. We don't have any alternating terms. So I'm not going to write the absolute value, but it's, later on, if you run into an alternating series and you can't tell about it, then you can use this as well. So this limit is just 2, because those are the same degree in the top and the bottom, and 2 is greater than 1. So the limit, that's the Greek letter rho, rho r for like ratio test maybe, I don't know. And then, just because root, that starts with an R as well, so I don't know. We know what n is greater than 1, or sorry, rho is greater than 1, so this series diverges. I think you'll see in a minute, but the ratio test is really good when you have factorials and you don't know what to compare it to. The comparison test is pretty good, but if we wanted to compare this to, say, like 1 over n, that kind of wouldn't help us because this is definitely smaller than that. Smaller than that. And, actually, we could have used the comparison test, right? This is smaller, and it's a p-series, and it diverges. So, well, we have 2 tests to tell us that. Diverges by ratio test, diverges by comparison test with 1 over n as well. Great. Okay, so really, let's look at example 2. So for this one, we're going to do the exact same thing, same instructions, with the same conclusions. So here we go. First, I would write down a sub n plus 1, and this is where I think people would get confused, so that's why I'm doing this. N plus 1 factorial divided by n plus 1 to the 9th. And then I'll go ahead and divide. So it'll be n plus 1 factorial divided by n plus 1 to the 9th times the regular sequence. Here we go. N to the 9th over n factorial. So what do we have here? We have, well, this is actually what I wanted to point out. N factorial, that's just n times n minus 1 times n minus 2 all the way down to 1, right? Well, let's say 3 times 2 times 1. You're just taking 1 away. You're getting lower and lower and lower, right? Hopefully that makes sense. Well, n plus 1 factorial is just the same thing with an n plus 1. Then take away 1, and then take away 1, and then take away 1 more, and more, and more. And so this actually simplifies to n plus 1 times n factorial, because that's what this is, n factorial. This is n plus 1 factorial. It's kind of nice that way. So then n plus 1 to the 9th, and that'll be, well, times n to the 9th over n factorial. The whole point was to get rid of that. That's what I wanted to do. Also, if I were to FOIL this out, I'm not going to, but if I were to FOIL this out, n plus 1 times n to the 9th. Okay, if I were to FOIL this out, I would get n to the 9th plus n to the 8th, like something with n to the 8th, maybe some other coefficients, but I'll get n to the 9th as my first term, and then something, 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 all the way down to just 1, because it'll be 1 times 1 times 1 times 1 9 times. So you could use the binomial theorem or Pascal's triangle to expand that quickly, but I don't care about that because of what happens. So if I took the limit of this, the limit as n approaches infinity, it should be the absolute value of this ratio, but I don't need that part because I don't have any negative terms. N to the 9th over n to the 9th plus, and then all these other terms in the middle, they have degree 8, a power of 8, a power of 7, 6, 5, 4, 3, all the way down to a power n to the 0. Hopefully that makes sense to you. So this is the highest degree term, and then plus 1. So, since this is the highest degree of 9, I'm going to multiply in the top and bottom just using my old trusty little limit techniques. And that goes away. That's nice. This goes to 1, and everything else, it would be like 1 over n, and then plus 1 over n squared, all in the middle there, all the way until we would get to 1 over n to the 9th. So, as I'm evaluating that, hopefully that makes sense as well. As I'm evaluating this, that goes to 0, 0, and 0. All of this stuff goes to 0. This part goes to 1. Great. And then we just have infinity. So that would be infinity plus 1 divided by 1, which is infinity, which means that this will diverge because it's greater than 1. The limit is greater than 1. So diverges by ratio test. And I'm going to stop at the video right there.